Hey guys, it's Arnav here, back with another Crash Course AP Chemistry video. Today we're going to be going over Unit 2, which is molecular and ionic bonding, and through the video we're going to go over the different types of bonds, how to make Lewis dot structures, and stuff of the same sort. And I just wanted to say thank you for clicking on this video and sticking with my channel. I know we only have 2 videos so far, but we're going to have a lot more, and we're going to make sure that you guys do great on your AP tests. Alright guys, so let's start this video by talking about the different types of bonds. So the 3 main types of bonds are ionic, covalent, and metallic bonds. Let's start by looking at ionic bonds. The 2 main traits of ionic bonds are that they form between metals and nonmetals, and also that they involve the transfer of electrons between atoms. Now, let's situate metals and nonmetals on the periodic table. So anything you see in green here, so like hydrogen, carbon, nitrogen, oxygen, these are all nonmetals. And anything including lithium and beryllium and under them, so basically the first 2 columns, they're all metals. And when they bond, you come up with an ionic bond. Now, an easy and quick way to find out if a bond is ionic or not is to see if the elements involved in the bond are from opposite ends of the table. And this is because nonmetals tend to be situated on the right hand side and metals tend to be on the left hand side. So if the elements in the bond are from opposite sides, it's most likely an ionic bond, right? Next, let's move on to the electron behavior in an ionic bond. And the main takeaway here is that electrons are transferred from one atom to the other. Let's look at an example of salt, NaCl. So normally sodium has 1 valence electron and chlorine has 7. But since chlorine is more electronegative than sodium, it's going to snatch away that 1 valence electron that sodium has to form a molecule of salt. So that displays the electron transfer that I was talking about earlier. Next, let's talk about how to determine if an ionic bond is stronger than another ionic bond. And it all comes down to the difference in charge. So using this table that dictates the charge for each separate column, what you can do is determine the difference in charge of the 2 elements involved in a bond, and the greater the difference in charge, the stronger the ionic bond. Now, I would really recommend you guys to memorize the charges for each column because it's really helpful in the AP exam. Now, let's talk about why I know that the difference in charge dictates the ionic bond strength. And the reason I know this is because of Coulomb's law, right? Based on last video, we talked about how the law of Coulomb states that the force of attraction between 2 entities is determined by the distance between them and also the the difference in charge between the entities. So I'm applying the same concept here where the greater the difference in charge, the stronger the ionic bond. Finally, let's talk about the physical characteristics of ionic solids. And the 4 main ones are that they tend to form crystal-like or crystalline structures, that they're brittle, they have high melting and boiling points, and also that they're good conductors of electricity when put into water. Now, the water part is really important because ionic solids cannot conduct electricity in solid or gaseous states. So yeah, I thought that was quite important. And finally, I've got an image here of commonly seen ionic solids in our day-to-day lives. Next, we have covalent bonds. Now, covalent bonds are kind of the exact opposite of ionic bonds in some ways in that they only form between 2 nonmetals, and also that instead of transferring electrons from one atom to the other, they tend to share electrons, right? So you can think of covalent bonds as this teamworky kind of bond, right? Now, moving on to physical characteristics, they tend to have a relatively low boiling and melting point as compared to ionic solids, and also they cannot conduct electricity in any state of matter whatsoever, right? Now, I would like to address the low boiling point because this low boiling point also means that covalent bonds are weaker than ionic bonds. And you might be asking, why is that? And that is because if you think about it, what does a high boiling and melting point signify? Well, basically, having a high melting and boiling point means that more energy is required to break a bond, right? And if more energy is required to break a bond, then you can conclude that it is stronger. So this is why ionic bonds are relatively stronger than covalent bonds as well. Now down here, I've got an image of 2 hydrogen atoms sharing electrons as they do in covalent bonds. And as you can see, they're sharing 2 electrons. And this is another thing that I wanted to point out. Whenever 2 atoms share electrons in a covalent bond, they always do it in pairs, right? So if they have 1 bond between the atoms, they'll share 2 electrons. If they have 2 bonds, they'll share 4, and so on. So you have to be sharing electrons in pairs. It's a big point. Next, let's move on to the 2 different subdivisions of covalent bonds. So even under covalent bonds, there are 2 types, and they are polar covalent and non-polar covalent. Now, to understand the difference between them, we need to learn what polarity is. And in order to learn what polarities, we need to go over electronegativity. So we know that electronegativity is the likelihood of an atom to, or an element rather, to really want an electron, right? So how likely is it for an element to just snatch an electron just out from somewhere, right? And we also know that the trend for electronegativity is that it increases from left to right and that it decreases from top to bottom. Now, using all of this, what polarity in a molecule basically is like a form of the molecule not being balanced. Now, I'm going to explain this with an example. Let's say you bond fluorine with oxygen, right? So fluorine is the most electronegative atom or molecule in the entire periodic table. So we know that what's basically going to happen is that even though fluorine and oxygen are sharing electrons in the middle, fluorine is going to have a stronger pull on the electrons, right? So this is going to cause the molecule to not really be balanced, and there's going to be kind of a pull where fluorine is going to be a stronger pull of attraction for the electrons being shared because it's pulling on them harder, and oxygen is going to kind of be a weaker pull of attraction. So that is what creates polarity, when one atom in the bond is more electronegative than the other. Now, I got another example of a polar covalent bond. We got carbon monoxide, where you have 1 carbon atom bonded to 1 oxygen atom. Now, in this case, oxygen is more electronegative than carbon. So, just like the last example, oxygen's pull on the electrons that are being shared is going to be stronger. So, since oxygen is pulling on them harder, there's going to be an imbalance causing for oxygen to form a pole that is more attracted to the electrons than carbon. Now let's look at an example of a non-polar covalent. Now, I have an example of just plain old O2, oxygen, that we breathe in. And the reason it's non-polar covalent is that it's made of 2 oxygen atoms. And since they're both oxygen atoms, they have the exact same electronegativity. And this applies to all non-polar covalent molecules. Basically, if both the atoms involved in the molecule have the exact same electronegativity, it's going to be balanced, right? Because they're going to have an equal pull on the electrons that are in the middle. So in order for a non-polar covalent molecule to come about, you need both the atoms to have an equal electronegativity. Okay guys, so one thing that I wanted to point out real quick is that for a non-polar covalent molecule to exist, the electronegativities don't have to be the exact same, okay? That's a mistake I just made like a few seconds ago. So there's kind of a range of electronegativity, right? So if the difference in electronegativity between the 2 atoms in the bond is between 0 and 0.4, that is quite small, and that will cause for the molecule to be non-polar covalent because the difference in electronegativity isn't that large. But if the difference in electronegativity is between 0.4 and 1.7 approximately, then that will make the molecule polar covalent because the difference in electronegativity is quite large. Now, on the AP exam, you really don't need to know these values, but it just might come up, so I thought you guys might want to know this. The third and final bond type that we're going to be looking at are metallic bonds. Now, metallic bonds only form between metals, and when I say metals, I also mean these transition metals in the middle. So metallic bonds are really this like mix and match bonding between these transition metals and also these 2 columns of metals. So just keep an open mind and consider all 3 like columns and group of transition metals in the middle when you're looking at metallic bonds. Now, here's an atomic diagram of what a metallic bond looks like. So you got your positive metal ions here, and then you got your electrons in the crevices between each adjacent ion. And on the AP exam, the best way to describe this is to talk about how a metallic bond has a sea of freely moving electrons. And this is because my teacher in chemistry and also a lot of others have told me that using this phrase guarantees you to get full points if asked to describe a metallic bond. Next, let's move on to the physical characteristics of a metallic bond, which are that the end product of a metallic bond tends to be malleable, ductile, lustrous, and also be a great conductor of heat and electricity. Finally, another thing to mention is that they have a high melting and boiling point, which means that they're strong, right? We talked about the significance of melting and boiling points just a few seconds ago. Before I move on to the next slide, I wanted to talk about why we did not have a charge assigned to all of these transition metals. And that is because depending on what these transition metals bond with, their charges keep changing. So we don't have a concrete estimate of a charge for them. Like for example, you know this first column will always have a charge of +1 and the second column will always have a charge of +2. But these just keep fluctuating, the transition metals. So that is why they don't have a charge associated with each of them. Alright, so our next topic of discussion is lattice energy, and this is something that only applies to ionic molecules, so just keep that in mind. So what is lattice energy, right? Lattice energy is basically the amount of energy that is required to convert 1 mole of any solid ionic molecule into its gaseous ions, right? So let's say you have 1 mole of salt. The lattice energy of that is going to be the amount of energy you require to convert that 1 mole of salt into its gaseous state, okay? Now, there are 2 factors that affect whether a molecule of an ionic solid will have more or less lattice energy. And those 2 factors are ion charge and atomic radii. So if the difference in charge of the 2 atoms in the ionic molecule increase, that's going to cause for the Coulombic force of attraction to also increase, right? Because difference in charge was one of the factors that affects Coulombic forces of attraction. And if the forces of attraction increases, that means that the lattice energy of the mole of ionic compound in question will also increase. And the other factor is atomic radii. So we know that as we move across the periodic table, atomic radius decreases, and as we move down, it increases. Now, what does a bigger atomic radii do? So I'm going to demonstrate with an example, right? Let's say you have 2 atoms with a really big atomic radii. Now, what that basically means is that they have so many electrons around them that the distance between them is so huge because of the huge cloud of electrons in the middle. But in contrast, if you take 2 atoms that have a relatively small atomic radius, they're going to have less electrons, which means that the electron cloud in the middle will be relatively smaller and the nuclei will be more attracted. So this is why a smaller atomic radius between the 2 atoms of an ionic molecule will cause for it to have a higher lattice energy. So to sum it up, if you have a greater difference in charge and if you have a smaller atomic radius, both of these contribute to your ionic solid having a larger lattice energy. Now finally, I've just got an image of what a lattice looks like. It's that cube-like structure and what an NaCl crystal looks like. So that's how sodium chloride is organized on a molecular level. We'll look at this deeper further into the video, but for now, that's like an intro for you guys. Moving on, our next topic of discussion is bond length and energy. And one thing to keep in mind before we start is that this only applies to covalent molecules and covalent bonds. So we already know that when 2 atoms bond covalently, they do so by sharing pairs of electrons. But something interesting is that you can have more than 1 bonds between 2 atoms. So you can have up to 3 bonds. And basically, I have this table below, and through it, I wanted to analyze with you guys the effect of having multiple bonds on other factors of the molecule. So here I have 3 diatomic molecules. I got H2, O2, and N2, and each of them have a separate number of bonds, and that is denoted by the bond order. So whenever someone says bond order, that is just the number of bonds within the molecule. So as you can see on the table, hydrogen's diatomic molecule has 1 bond, oxygen has 2, and nitrogen has 3. And if you take some time to review the relative length of the bond and the images, there's a common trend that comes up, right? And the trend is that as you increase the bond order or the number of bonds within a molecule, that decreases the internuclear distance between the 2 atoms. And this is because as you increase the number of bonds, you are increasing the force of attraction between the 2 atoms in question. And another thing is that as you increase the number of bonds, you're also strengthening the bond between them. So let's say you have a molecule with 3 bonds connecting the 2 atoms and another molecule with just 1 bond connecting the atoms, the molecule with 3 bonds will be way stronger than the molecule with just 1 bond. Now, next up we have a graph for this unit. I believe this is the only graph we have this unit, so that's good for you guys. In the graph below, we're basically analyzing internuclear distance versus potential energy and how that affects a molecule. So at the lowest point, right about here, is in most stable state, and that is basically where a molecule tends to exist. Now, this one's just a generic graph, so we're not looking at any molecule specifically, but yeah, let's just call it the molecule, okay? So this is where the molecule exists, right here. And through the graph, we can see what happens as we increase internuclear distance and as we decrease internuclear distance. So we can see that as we increase internuclear distance, we're increasing potential energy. And the reason between that is, let's think about it like this. You have a molecule, right, with the 2 atoms. So as you're increasing internuclear distance, what you're effectively trying to do is pull it apart, right? And to do that, you have to overcome the attractive forces between the 2 atoms. And again, to do that, you need to put in energy. So energy is required to break the bond apart and pull the atoms apart from each other, right? So that is why the potential energy keeps increasing. And you might be wondering why the potential energy just hits 0. By the way, this is 0. Just plateaus and hits 0 at one point. And that is because beyond one point, the atoms are so far apart from each other that they just don't associate with each other and have no forces of attraction that are keeping them together. Now let's look at the other way. What happens as we decrease internuclear distance? Now this might be funny to some of you guys, but as we decrease internuclear distance, you'll notice that potential energy is again increasing. And this is because as we have attractive forces, we also have repulsive forces. So as we know, when you have 2 atoms, you have electrons around them, and there's kind of an electron cloud in the middle, right, between the 2 atoms. And as you push them closer and closer to each other, the electrons start to repel each other because there's a certain distance beyond which they don't want to get too close. And if you want to overcome these repulsive forces, you have to keep on putting in more and more energy to push them even closer together. So this is why potential energy increases the other way as well. Finally, one thing I wanted to point out is that this vertical distance between the lowest point on the graph and the x-axis is known as the bond energy, and it is the amount of energy that is required to completely break the bond. In this case, the bond energy is 436 kilojoules per mole, which is the unit, and that is because that is the distance between the x-axis and the lowest point. Now, I would like to do some questions with you guys to really drive home this concept. So here we have a graph, and I have some questions relating to the graph. All right. So the first question is, what happens to potential energy of the stable state as we move from graph B to graph A? Now, as we just talked about, the stable state is the lowest point on the graph. So what the question is really saying is, what happens to the potential energy as you move from point B here to point A here on each of the graphs? Now I'll give you guys some time to answer. Okay, I'm assuming you guys have tried. Now the answer is it decreases because, as you can see here, the potential energy is getting even more negative. Now, while real questions are going to be a bit more different to this, I just thought this exercise would help you guys navigate better on the energy curve of this diatomic molecule. Now, moving on, we have, does graph B or graph C have a comparatively higher bond energy? Now, as we talked about, bond energy is the vertical distance between the lowest point on the graph and the x-axis. So I'll give you guys some time to find out which one has a higher bond energy. Okay, so if you guys said graph B, you're correct, because as we can see here, the vertical distance between the lowest point on graph B and the x-axis is greater than that of graph C. So therefore, graph B has a higher bond energy, and the molecule that's represented by graph B has a higher bond energy. Okay guys, moving on, the next part of this video is going to constitute drawing and representing ionic solids. So I've made 3 example diagrams of ionic solids, and I want you guys to just take a look at them, and then we're going to discuss some common themes that we notice across all of them, alright? Okay, so here are the 3 diagrams I made, and here are the main takeaways. So you always want to make sure that the positively charged ions and the negatively charged ions are right next to each other, and they keep alternating. Now this is something you see commonly throughout all 3 diagrams, and it is also something that is mimicked by actual ionic solids on a molecular level. Moving on, another thing to talk about is how each ion size is independent of the other one. So what I'm basically trying to say is that just because the positive ion is big or small doesn't mean that the negative ion is also going to be big or small. It all comes down to atomic radius. So make sure that whenever you're making an ionic solid, you look at the ionic radius of each of the elements that are a part of the molecule. So for example, if I'm making an ionic solids drawing and the solid I'm looking at is salt, right? I'm going to go to the periodic table and I'm going to look at the ionic radii of both sodium and chlorine and make my diagram accordingly. Finally, I wanted to point out that all of these structures form lattice-like structures, and that is something that I just found interesting and want to share with you guys. So I have some practice problems for you guys to try. First, I have made a data table with two different elements and their ionic radii, and what I want to do, or what I want you guys to do, is try and draw the ionic solid diagram. Okay, so as the example I used on the last slide, the solid here is going to be salt or sodium chloride, so take your time. All right, now something you'll notice in the answer is that sodium has a relatively larger ion size in comparison to chlorine, right? Which is that the positive ion is larger than the negative ion. And that is because, as is stated in the table, sodium has an ionic radius of 227 picometers, while chlorine has an ionic radius of 175 picometers. And by knowing that sodium is going to have a larger ionic radius, we're going to represent it larger on the particular diagram. I've got another question for you guys. So basically here, there's an ionic solid, a mystery ionic solid, that is composed of strontium and another unknown metal. And I want you guys to figure out what this unknown metal is. So I've got a couple of hints for you guys before you attempt this. The first one is that whenever you're dealing with ionic solids, it all comes down to charge, right? So all you need to do is first find the charge of strontium, which is going to be +2. And then you want to find a non-metal that has a charge of -2, right? To neutralize out the charge of strontium and form an ionic solid. So I'm going to give you guys some time for that. All right. So I know I've said any non-metal in group 16, and what that basically means is any non-metal in this column right here. So that's oxygen, sulfur, or selenium. And that's because they all have a charge of -2, right? So they would all make suitable elements for strontium to bond with. And this is another piece of terminology that I wanted to go over. So basically on the periodic table, every column is known as a group and every row is known as a period. So just keep that in mind for the future. Moving on, the next topic we're going to be covering are metals and alloys. So by definition, what an alloy is it's basically a mixture of a bunch of elements, and at least one of those elements has to be a metal. So in AP chemistry, the most common types of alloys you're going to be looking at are either a mixture of two metals or a mixture of one metal and another element that's not a metal. So there's also two different subdivisions of alloys. Let's take a look at them. The first type of alloy is an interstitial alloy. Now, the main characteristic of an interstitial alloy is that the two elements being used in it have atomic radii that are very different from each other. So here I have an example of steel, which is made by combining iron atoms and carbon atoms. Now, as you can see based on this diagram, iron has a very large atomic radius in comparison to carbon, and this is why steel is an interstitial alloy. The second subdivision of alloys is substitutional alloys. As opposed to interstitial alloys, substitutional alloys have two elements that have very similar atomic radii. So one example is brass. And as you can see in this diagram, both copper and zinc have very similar ionic radii. This is why brass is a substitutional alloy. Now, one thing I wanted to point out before we move on is that both interstitial and substitutional alloys can have more than two elements, as I pointed out in the definition of an alloy. But you will more commonly only see mixtures of two elements in alloys in the course of AP Chemistry. So I have a practice problem for you guys to try out. So basically, if the identity of one of the metals in the interstitial alloy is copper, which of the following could be the identity of the unknown metal? So I have drawn out a representation of this unknown alloy, and the big circles are copper, right? So what I basically want you to do is figure out the identity of the small circles in the middle. Here are your options and a periodic table. One thing I would like to point out is that given the big difference in atomic radii, we already know that we are looking at an interstitial alloy, right? So a good tip I have for you guys is to really find out which of the following metals at the bottom have an atomic radii that's really small in comparison to copper, and that is most likely going to be the right answer. Okay, I'm assuming you guys have given it a shot. If you guys said titanium, you're correct, because of all the following options, titanium over here has an atomic radii of about 47, and copper has an atomic radii of about 63. And since titanium has such a small atomic radii compared to copper, it fits the description of the diagram really well. But let's just take a look at the other choices to make sure why they're not right. First up, we have zinc. And zinc is right over here, on the right of copper, sorry. And therefore, zinc has a larger atomic radii than copper, which is not something we're looking for. Then we have nickel and silver. Nickel is on the left of copper, right? But it is still quite close to copper in terms of atomic radii. Silver, on the other hand, has a way larger atomic radii than copper, and cadmium also has a way larger atomic radii. So in the end game, titanium is the best choice for us to pick. Alright guys, so the next portion of this video is going to be drawing out Lewis dot structures, and before we dive into how to actually draw them, I wanted to go over a skill that I thought was important, which is determining how many valence electrons an element has. So the first step you're going to do is basically ignore all these transition metals as they're not relevant to this valence electron concept. And the trend is that this first column of elements has one valence electron, and as you keep moving to the right, ignoring these transition metals in the middle, you keep adding one valence electron. So this first column has one valence electron, the second column has two valence electrons, this third has 3, this fourth column has 4, and then 5, 6, 7, and finally you will end with 8 valence electrons for this final column of noble gases. Now let's go into what a Lewis diagram is and how to actually draw it. A Lewis diagram is a way to represent how the electrons between atoms attract when they're actually bonding to form a covalent bond. And when making them, there are two things that I would recommend you guys keep in the back of your head. The first one is that when an atom bonds covalently, it wants to make sure that it is surrounded by 8 valence electrons, as that is its most stable form that it can find in that given bond. But I wanted to go over something else. There are a lot of exceptions in AP chemistry, right? So this 8 valence electron or octet rule has a couple of exceptions that I'm going to go over soon. The second thing that I think should be kept in mind is that whenever valence electrons are shared, they're shared in pairs. So this is just an example I'm giving, but basically say like a carbon is bonded to another carbon, right? If it has just one bond between them, that is the same as this carbon having 2 valence electrons and this one also having 2 valence electrons. And that's because they're sharing it, so they can both count them as their own electrons. Now let's move on to the step-by-step procedure of how to actually draw a Lewis diagram. So the first step would be to count the total number of valence electrons in your molecule by looking at the individual atoms and the number of each atom in your molecule. Next up, you want to determine the orientation of your molecule, and this is basically when you have a central atom in a molecule and then other atoms surrounding it. That's the general structure of a covalent bond. And one tip that you can use is that the atom with the lowest subscript in the bond is the one, or in the molecule rather, is the one that goes in the center of the bond. So for example, if you have H2O, since the oxygen has the lowest subscript, you're going to put it in the middle and surround it with 2 hydrogens. Next up, you want to create like a rough sketch where you just connect the central atom to the outer atoms with one line each. And a line is basically a bond, right? That's what it represents. So just keep in mind the number of electrons you've used up, as each bond is the same as using up 2 electrons. Finally, you want to complete the diagram by adding electrons around atoms as needed and also making more bonds if necessary. Now the adding electrons part might be confusing, but we're going to go over that in our next example. But before we move on, let's go over the exceptions, right? So AP Chemistry has a heap loads and tons of like exceptions to every rule there is. And it really drove me up a tree in class, but let's go over them real quick. So the exceptions are as follows. The first one is that hydrogen, right? It just completely destroys the octet rule. So normally you know how you need 8 electrons to be stable, right? Hydrogen only needs 2, which I don't know why, but it only needs 2. Second up, we have helium, which also only needs 2. And then we have beryllium, which only needs 4 valence electrons to be completely stable. We have boron, which needs only 6. And then there's this final exception that's gonna completely blow your mind, but we're gonna do that on the next slide, okay? So if we're gonna draw out water, first we're gonna count up the total number of valence electrons in the molecule, which is going to be 8. Then we're gonna find out which atom goes in the middle, which in this case is oxygen, since it has the lowest subscript. Then we're gonna draw a rough sketch by combining each of the atoms by basically drawing a line and connecting them, which is symbolic of a bond. And finally, we're going to add the remaining electrons as necessary. So in this left diagram, keeping in mind that each bond is basically equal to 2 electrons, we have used up 4 since we have 2 bonds. But we still have 4 valence electrons left. And what we basically did with them was we put them around oxygen. Now, these are known as lone pairs, and they are basically put around atoms that still don't have an octet of electrons after you're done with this rough step. So let's see why this Lewis dot structure works. So when sharing electrons, hydrogen has 2, so hydrogen is happy. This other hydrogen also has 2, so it's happy. And this oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So this also happy. So that's why this Lewis diagram works. Next up, we're gonna make a Lewis diagram for BrF4-. Now, the minus might be a bit daunting, but all you do with that is you just add it to the sum of all the valence electrons. So we know bromine has 7 valence electrons and fluorine also has 7 valence electrons. So what we're going to do is we're going to do 7 plus 7 times 4 because there are 4 fluorines, which is 35. And we're going to add another valence electrons because this molecule, or this ion rather, is negatively charged. The next step is to find out which atom goes in the middle, which in this case is bromine due to it having the smallest subscript. Next, we make a rough diagram, and we notice that even though bromine is happy having all of its 8 valence electrons, the fluorides are not because they only have 2, and they need that octet to be complete. Now, forget the middle, okay? That's the exception I'm going to explain in a bit, but let's talk about the fluorine. So, given that you've used up 8 valence electrons here, you still have 28 left, and the first step you're going to do is you're going to make all the fluorine happy, right? So you're going to add 6 valence electrons to each of them because that'll help them complete their octet, because you're going to have 2, 4, 6, and then this bond is 8, and they're all going to be happy and stable. So if you do that to each fluorine, you use up 6 times 4, which is 24 valence electrons. But you originally had 28 valence electrons to begin with, and you used 24, so you still have 4 left. Now, this is the exception, right? Basically, if the atomic number of the central atom is greater than 14, so basically any element beyond phosphorus, what you can do is you can add all of the excess electrons to the central atom. So in this case, I've added all the remaining excess electrons to bromine in the middle, as we just had some lying around, right? And we have to put them somewhere. And finally, the reason I've put brackets and a minus around this molecule is that's just standard notation, given that the original molecule was also negatively charged. Next up, the concepts we're going to be going over are resonance and formal charge. And this whole concept stems from the fact that sometimes there are more than one ways to represent molecules using Lewis dot structures. In this case, we have nitrous oxide, and as you can see, there are 3 different ways to represent nitrous oxide, with each way working well and doing justice by giving each atom in the molecule its full octet of electrons. But in reality, some of these molecules, or rather some of these Lewis structures, are more stable than the others. And what that stability allows for it to do is basically, if you're more stable than the other Lewis structures, you contribute more to what the molecule actually looks like in nature. Because if you think about it, nitrous oxide can't have 3 variants, right? It's gotta look like one of these. And basically the most stable version of these 3 is the one that's gonna contribute most to what nitrous oxide looks like in nature. And that is the whole concept of resonance, right? You basically have 3 or more, or however many Lewis diagrams that you can make for any molecule, And out of them, you come up with like a sort of average or hybrid depending on each Lewis structure's abundance and stability. In this case, the way nitrous oxide looks in nature is like this. And you might be wondering that this is the exact same as the third Lewis structure. And that is because it is the most stable, right? As I just talked about, stability is a big factor in determining what the hybrid looks like. And in order to determine the stability of each specific Lewis structure, we use a concept known as formal charge. So what we do in formal charge is basically we use this formula, which is number of regular valence electrons minus number of valence electrons once bonded, to calculate the charge of each specific atom within each specific Lewis diagram. And what you want is for a diagram to have the least amount of charge. So you want it to have 0 charge on each atom, and that one's going to be the most stable. Now, let's say you have 2 Lewis dot structures that you're comparing, right? And they both have charges of 0 on most atoms, but they have negative charges on separate atoms. Now, in this case, the more stable Lewis dot structure will have the negative charge be on the more electronegative atom. You guys will see this come into fruition during our example. Now, before we do the example, I wanted to go over how to calculate the number of valence electrons once bonded with you guys, right? So this is the molecule in question, and I want you to calculate the number of valence electrons once bonded in oxygen. Now, here's the trick to doing this, right? Since oxygen here has 3 lone pairs, we know off the bat that it has at least 6 valence electrons once bonded. But then you have this pair under oxygen, and some of you might be tempted to say it's a pair, right? And a pair is the sharing of 2 electrons, so that's 2 more valence electrons. Well, that's not really the case, because even though oxygen is bonded to carbon and the sharing of those 2 electrons is helping it complete its octet, in reality, only one of those valence electrons actually belongs to oxygen. So in this case, oxygen is going to have 3 lone pairs, which is 6, and 1 valence electron from that bond. So 6 plus 1 is 7, right? Now, let's do the same thing for this hydrogen down here at the bottom. That's double bonded to the carbon. Now, once again, each bond is worth 1 valence electron. So once bonded, that hydrogen is going to have 2 valence electrons. That's correct. Now let's do our example. All right, let's get on with the example then. So I've given you guys 3 resonance structures for the cyanate ion, and I want you to calculate the formal charge of each individual atom in the molecules. So then we can cross-compare all of them and find out which one has the least overall formal charge, and that is the one that's going to be our most stable structure, and therefore contribute the most to the resonance hybrid, right? Because as we talked about earlier, stability is a big factor in determining how much does a Lewis dot structure contribute to the resonance hybrid. So yeah, I've given you guys the formula for formal charge and also a periodic table to figure out how many valence electrons each of the following atoms in the molecules have. And I'm going to do the first molecule with you guys just to like help you guys with an example and give you time to do the remaining 2. So yeah, let's get on with it. In this first molecule here, oxygen, we know oxygen regularly has 6 valence electrons, right? And once bonded, it has 1, 2, 3, 4, 5, 6. It also has 6. So 6 over here minus 6 over here, that's 0. So in the first molecule, the oxygen has a formal charge of 0. Moving on to carbon, carbon regularly has 4 valence electrons, and once bonded in this molecule, it has 1, 2, 3, 4, also 4 valence electrons. Now, if you guys are wondering, this goes back to what we did on the last slide, right? Where each bond is normally worth 2 electrons because you're sharing, but when it comes to formal charge, it is only worth 1 electron with respect to one specific atom. In this case, our specific atom is carbon, and therefore each of these bonds is only worth 1 valence electron. So 4 regular minus 4 once bonded is 0 again. Finally, we have nitrogen. Nitrogen regularly has 5 valence electrons, but in this case, it has 1, 2, 3, 4, 5, 6. So the 5 it regularly has minus the 6 it has once bonded is going to be -1. Now I'm going to give you guys a second to calculate the formal charges for the rest of the atoms on the remaining 2 molecules. Alright, I'm assuming you guys are giving it a shot, so these are the answers. And once again, I just used the formula and plugged in the number of regular valence electrons minus the number of valence electrons that each atom has once it has bonded within the molecule. Now we can rule out this middle resonance structure, and that is because it has the highest overall charges, right? These outer ones have two atoms that have a charge of 0, or rather a formal charge of 0, and one atom with a formal charge of -1 each. But this one has formal charges of +1 and -2. So the magnitude of charges is the greatest for the middle one, so we're just going to remove it. That cannot be the resonance structure that contributes the most to the hybrid and therefore is the most stable. So what we're doing now is just looking at the outer resonance structures, right? The one on the left and on the right. Now, you might be wondering how to determine which one is more stable. And what you want to make sure occurs in the more stable one is that the negative formal charge falls on the more electronegative atom. So in this case, we're looking at nitrogen and oxygen. And which one is more electronegative? Well, it's going to be oxygen, right? Because we know through periodic trends, as you move towards the right of the periodic table, you keep on getting more and more electronegative. So because of that, the third resonance structure is going to be the most stable and therefore contribute the most to the resonance hybrid, which is how this cyanate ion would actually occur and look like in nature. Moving on, we have the concept of VSEPR and bond angles. And what VSEPR basically is it's this theory that allows us to predict the exact angle between two bonds, right? So for example, I've given you guys a list of all these molecules, and we already know the bond angle between each consecutive bond. And why is that? It's because scientists and chemists alike basically came up with different geometrical shapes for each molecule, and using that under a microscope, they just found the bond angle, right? And our job as AP chemistry students is just figuring out what the geometrical shape is, right? The bond angles are something that are just given to us beforehand, so we're required to memorize them and just write it down. But as I just talked about, our main job is figuring out what the geometric shape is. So really focus on distinguishing each geometric shape from the other one. And another thing I wanted to go over before we actually start looking at these different geometric shapes is what a domain is, because domains are used to separate these geometric shapes into different families and categorize them so they're easier and more understandable, right? A domain is basically either a lone pair or a bond. So as you guys can tell, each of these have two valence electrons, right? Lone pair has two, and a bond is composed of two shared valence electrons. So just know what a domain is. First up, let's look at bond geometries that have two domains, right? Here we have a linear geometry, a linear VSEPR geometry. As you can see, it has two domains in the form of two bonds, and it also has a bond angle of 180 degrees between the two bonds. Moving on, let's look at families with three domains. First up, we got the trigonal planar VSEPR model. In this case, the three domains are in the form of three bonds between the central atom and the outer atoms, and the bond angle between each of the bonds is 120 degrees. Next up, we have this model, and this is known as a VSEPR bent shape, so bent, right? And the reason it's bent is because the three domains in this situation are two bonds and one lone pair. So what a bent model is, it's a regular linear model, right? So it's going to look like this, but you add a lone pair on the top, and what that lone pair does is it creates repulsive forces between itself and these bonds here and causes the regular linear model to basically bend down. And that is what causes the bend within a bent structure. So that lone pair is bringing about repulsive forces basically. And the bond angle in this scenario is 109.5 degrees. So just remember that, right? These bond angles are something you guys really want to memorize. Next up, let's look at families that have 5 domains, or geometric VSEPR families that have 5 domains, right? First up, we have a tetrahedral VSEPR model. In this case, all the 4 domains are in the form of bonds, and the bond angle between each of the following bonds is 109.5 degrees. Moving on, we have a trigonal pyramidal VSEPR model. In this case, the 4 domains are in the form of 3 bonds and 1 lone pair up top. And that 1 lone pair up top, again, creates repulsive forces, causing for all of the bonds to kind of move down a little bit, which brings about this pyramid-like shape. And finally, the bond angle within a trigonal pyramidal VSEPR model is 107 degrees. This is another final model within the family of 4 domains, and this is another VSEPR bent model. And the reason that it has an even smaller bond angle than the other bent one is you just added another pair of electrons on top, so another lone pair on top. And as you keep adding lone pairs on top, that causes more repulsive forces to come about, and the bent model bends down even more, which shrinks the bond angle between them, which is why in this case the bond angle is 104.5 degrees. Moving on, we have VSEPR model families that have 5 domains. So the first shape within this family is known as a trigonal bipyramidal VSEPR model. Here we have 5 domains in the form of 5 bonds, and the bond angles are 90 degrees and 120 degrees. Another VSEPR model within this family is known as a seesaw. Here the 5 domains are in the form of 4 bonds and 1 lone pair up top. This VSEPR model kind of resembles a seesaw, which is why it's called a seesaw model. And another thing to note is that the bond angles are slightly under 90 degrees and slightly under 120 degrees. And you might be wondering what specific bond angle to write on the AP exam when it's slightly under 90 and 120. So one tip I have is don't write that the bond angle is less than 90 degrees on the exam. They will not give you points for that. What you should do instead is just guess any number that's slightly under 90 or slightly 120. So 89 or 119, because they have this set range on the AP exam, and if your angle is within that range, they'll give you credit for questions like this. This is a tip that my AP Chem teacher gave me, and it was really helpful at the exam. The next VSEPR model within this family is known as a T-shaped VSEPR model. And it's pretty self-explanatory why it's called T-shaped, right? It looks like a T. And the 5 domains in this case are in the form of 3 bonds and 2 lone pairs. And finally, the bond angle for this specific VSEPR model is slightly under 90 degrees. So again, write anything that's under 90, but still very close to 90. So 89, 88, something like that. And you guys might be wondering that since we add another lone pair to the bent model that we saw at first, what happens if you add a third lone pair to a bent structure? Well, it becomes linear, right? So basically at this point, when you add a third lone pair, the repulsive forces kind of start acting weirdly, and it causes for a linear pair to come about. So just know that if you have a molecule that has 5 domains in the form of 2 bonds and 3 lone pairs, is going to have a linear bond angle, so 180 degrees. Finally, we have VSEPR models that have 6 domains, right? First up, we've got the octahedral VSEPR model. So over here, all the 6 domains are in the form of bonds, and the bond angle is 90 degrees. Pretty simple, not too complicated. Next up, we have square pyramidal. And this VSEPR model has, again, 6 domains in the form of 5 bonds and 1 lone pair. Just like the trigonal pyramidal structure we saw earlier, it also kind of looks like a pyramid, right? And the bond angle is a bit under 90 degrees, so as I said earlier, write something like 88 or 89 on the AP exam. Do not write less than 90 degrees. You will not get credit for that. Next up, we've got the square planar VSEPR model. And this has, again, 6 domains, but here it's in the form of 4 bonds and 2 lone pairs, 1 on top and 1 on the bottom, which is why it's kind of smushed, right? Because these lone pairs are kind of placed opposite to each other, so their repulsive forces are kind of equally distributed, and it's kind of smushed. The bond angle in this case is going to be exactly 90 degrees, so it's not less than anything, just know it's 90. And now I have a question for you guys, right? Now that we've gone over all the different VSEPR models and families, I want you to figure out what VSEPR structure a methane molecule displays. So I've just written down a few things for you. Methane has 8 valence electrons in total, right? And carbon is going to be the central atom since it's the most electronegative. So the first thing you do with questions like this is you draw out a Lewis diagram. So as we can see, we've drawn a Lewis diagram. And another thing to notice, it has 4 domains, right? Because it has 4 total bonds, and that means it's 4 domains, no lone pairs, just bonds. So 4 domains. And since there are no lone pairs, using our memory of the different VSEPR models, we should off the bat know that it is tetrahedral. Now, you guys might not have gotten this, and don't worry at all, right? Because it takes a while for you to really memorize all the different Western models, but I would highly recommend learning what each of them look like, their name, and 100% memorizing their bond angle, because it's really quick to do that on the AP exam and saves you a lot of time. So next up, we have the concept of bond hybridization. And this is again only relevant to covalent bonds. What basically happens sometimes is when an atom or of any specific element, right, bonds within a molecule, what happens is that contrary to the regular orbitals we're aware of, like the s, p, d, and f orbitals, right, from electron configuration back in Unit 1, instead of those orbitals bonding to form bonds, what happens is new hybrid orbitals are formed. And that is why this concept is known as bond hybridization, because hybrid orbitals are forming. In the case of AP chemistry, the only 3 hybrid bond or orbital formations we go over are sp, sp2, and sp3. And in order to calculate the bond hybridization of a specific atom in a molecule, we need to learn what a sigma and pi bond is. So I've used this image to demonstrate, right, what a sigma and pi bond is. Basically, any single bond is known as a sigma bond, right? So between hydrogen and carbon, we have a sigma bond. Between here, again, we have a sigma bond. And here's where it gets interesting. Between these 2 carbons, we have a sigma bond and a pi bond. So since we have one bond to begin with, right, between them, that bond is going to be a sigma bond. But any bonds that we have on top of a single bond are known as pi bonds. So in this case, we have one sigma bond and one pi bond. But in this case, we have one sigma bond because there's a pre-existing bond, and then two pi bonds, because on top of that first bond, we have 2 more bonds between the 2 carbons. So again, one sigma bond, 2 pi bonds, one sigma bond, 1 pi bond. So first you calculate the sigma bond, and the remaining bonds are all pi bonds. And the reason I taught you this is to calculate hybridization, you need to know how to calculate the steric number. And the steric number is basically the number of sigma bonds that the specific atom has, plus the number of lone pairs the specific atom has. And the way you work this is you use this table. You might have to memorize this table. I'm sorry, I know it's for memorization, but this is a really easy way to calculate bond hybridization. So once you calculate the steric number of the specific atom you're looking at, if it aligns with any of these steric numbers, so 3, 4, or 5, you're gonna have the following hybridization. So let's do some examples, right off the bat. Here, let's look at this central carbon atom, this one right here. So this central carbon atom has 4 bonds. And since these 4 bonds exist, they're sigma bonds, right? Because we're only looking at sigma bonds is what I'm trying to say. We're not looking at pi bonds. So it has 4 sigma bonds and no lone pairs. So we're just going to have a steric number of 4, which means a hybridization of sp2. So in this case, this carbon atom has a hybridization of sp2. Moving on, let's look at this carbon atom. Here we have 3 sigma bonds and 1 pi bond here, but we don't care about the pi bond, right? That is just a concept I taught you guys to identify later on the exam. That's just something you need to know. So going back to what we were talking about, we have 3 sigma bonds here, 1, 2, 3, but no lone pairs, right? So our steric number is going to be 3. And a steric number of 3 is a hybridization of sp. And that is the hybridization of this carbon. So similarly, just use the formula for steric number and this table to just come up with the hybridization of a specific atom within a molecule. Alright guys, thank you so much for watching the video, and I hope it really helped you guys. In the description below, I have linked a link to this presentation, and if you have any questions beyond that, I also have my emails and the comment section down below. So yeah, don't be afraid to reach out, and thank you so much for your time, and hope the video helped you out. Bye.